Hello everyone. In today's lecture, we'll be looking at all the equations that we've derived so far. It's a summary of all the equations in the bulk, as well as the equations at the interface, the boundary conditions at the interface. And this will set the stage for launching into newer topics in this course. So let me begin by first reminding you of what are the kinds of fluids that we'll be looking at. As I've already reiterated several times, we'll be looking at incompressible flows, and the fluids that we'll be looking at are all Newtonian fluids. Okay, there are several advances in interfacial fluid mechanics involving non-Newtonian fluids, but that will be too advanced in a course like this. So to illustrate the equations and the boundary conditions, I have taken a simple geometry. So here's a system that I'm looking at. So this is basically a flow between two walls. It could be two-dimensional or three-dimensional flow, and there is an interface separating the two fluids. So we'll call this fluid 1, and we'll call it as fluid 2. And at the interface separating the two fluids 1 and 2, we have a surface tension. In general, the surface tension need not have a constant value. It could be vary in space. Okay, so let's first look at the equations in 1 and 2. Okay, this 1 and 2 sometimes can also be referred to as fluid minus fluid and plus fluid. Okay, so let's look at the equations in the two phases. Equations in fluid 1 would be del dot u for fluid 1 is 0. That's the continuity equation. And we have the Navier-Stokes equation for momentum equation, that is by del T plus, that's a convective term, the pressure term U. So here the viscosity is U1 and there is a density rho 1. And the velocities are all for fluid 1. So we'll put a superscript 1. And this pressure is also for fluid 1. Similarly, we have for fluid 2, which I will write it with green, we have del dot U for fluid 2 is 0. That's a continuity equation. Density that's the inertial terms plus the viscous terms. So these are the equations in both the fluids. In addition, we can also put in a gravity term, either in fluid 1 and fluid 2 both, or only in one of the fluids. But when we actually solve problems with such as thin flows of thin films and so on, we will actually introduce this gravity term later. Okay. The boundary conditions for fluid 1 would be the no slip condition, which would mean that the tangential velocity u dot t would be 0. Okay, and we have the normal velocity, which I'll just call it as un, is 0. This is for fluid 1. So no penetration condition and no slip condition at the wall. Similarly, for fluid 2, we have u dot t is 0 for fluid 2, and we also have un for fluid 2 is 0. The no slip and the no penetration condition. Now, what about interface conditions? For the interface conditions, we have the jump conditions in the interface, which I've already discussed. So instead of calling it as minus and plus, let's call this as fluid 1 and fluid 2. We have the jump conditions at the interface. So these are the conditions that you'll have at the interface. In addition, you will need a few more conditions, such as continuity of velocity at the interface, The first one is continuity of velocity, of tangential velocity. So that will be ut1 is ut of 2. Now there could be two components of this velocity, which is a three-dimensional flow. Otherwise, you just have, in two-dimensional flow, it's just the tangent that you see along the interface. Okay, and we also have the normal velocity is related. The normal velocity on both sides is also related. So you have density times un minus wn plus is equal to, or 2 is density un minus wn 1, where wn basically is the position of the interface. And then we have the normal stress balance at the interface. So the normal stress balance at the interface is just this condition here. And then we have the tangential stress balance at the interface. So having written down all these equations, we have a system of equations for the velocity and the pressure. We will need to also know how surface tension is varying in position. If, for example, if surface tension is varying in space, then the right hand side term in the normal stress, in the tangential stress balance, the Marangoni term is non-zero, and that leads to a discontinuity in the tangential stress. We will need to know how surface tension itself is varying in space. Okay, so for example, for variable surface tension, problems, we will have to determine how surface tension is changing with position. With position, I'll call it as x bar. For example, you could have two possibilities. Okay, so for thermal Marangoni flows, the surface tension gamma is typically a function of temperature. Okay, so for various systems, for various interfaces, these results are typically available in the literature, and one needs to know what's the dependence of gamma with temperature. For example, the simplest dependence one can think of is a linear dependence. So as you heat up the interface, the surface tension reduces, and as you cool the interface, surface tension increases. So you could have a linear relationship between surface tension and temperature. So it would be something like this. Okay, where gamma is basically this and temperature is this. This is the linear relationship. You could have more complex relationships. Okay, if surface tension is varying as a function of temperature, then you need to also determine what is the temperature at different parts of the interface. Correct? So to understand what is the temperature at different parts of the interface, for these kinds of flows, we are required to determine the temperature distribution in the flow. For example, temperature can get heat flux can get transported from one place to another either by conduction effects or by convection effects. So this is now a coupled problem. So we will have, in addition to, we will have two more equations. An equation for evolution of the temperature field, typically in both the fluids, evolution of equation of temperature fields in both the fluids, and then a coupling between temperature and surface tension. Once we do this, the system is what we call as closed. We have now several equations. We have the momentum equations and the mass balance equations in both the fluids. We have necessary boundary conditions at the interface and at the walls or at infinity. And then finally we have, if surface tension is varying, we know how it is varying. For example, it could be varying because of temperature. If it's varying because of temperature, we can call it as thermal Marangoni flow, because the temperature gradients, the Marangoni flow that is generated is because of temperature gradients. And for that we will need two more equations. One, an equation for temperature, and two, a relation between surface tension and temperature. Okay. So similarly, we also have what is called as solutal in this case, gamma, the surface tension, could be a function of some concentration. The concentration in this case could be surfactants at the interface. So for example, I will again need an equation of state. This is, again, there are two concentrations one has to keep in mind. This is concentration of the interface. Okay, this is concentration of surfactants at the interface. So once I know the interface concentration, I determine what is the concentration, how surface tension is varying with concentration. So typically what you will find is that as you increase the concentration, surface tension drops. So you have a typical curve which looks like this. So at large concentrations, surface tension reaches a saturation value, and at very, very small concentrations, again, surface tension reaches a saturation value for the clean interface. Clean interface as in, what is the surface tension in the absence of surfactants? As an example, for water, the surface tension value is 72 millinewton per meter. This is for a clean interface. Clean interface meaning the interface between air and water does not have any surfactants, no contaminants, no surfactants. And then you can add soap to this system or surfactants to the system, and surface tension would continuously drop. Okay. And for every concentration, you can determine what is the surface tension. There are various ways to do this. I will not be able to go into details of how this is done, but we will have I will briefly discuss how surface tension itself is measured, and then we will maybe, if there's time, we'll touch upon this particular a curve, something like a curve of this nature. But again, we will need to know how equation surfactants are evolving at the interface. So we could have an equation for Ci. So this could mean that we have an equation for Ci at the interface. So typically surfactants are not only at the interface, but most of the surfactants are soluble in the bulk. Okay, so you could have a concentration of surfactants in the bulk. So you could have an equation for a bulk concentration, which I'll call it a Cb in the bulk. And then finally, relationship between gamma and concentration at the interface. So the picture that I want you to imagine is that you have an interface and you have surfactant molecules in the bulk, and every now and then these surfactant molecules will, because of their very nature, because they have a hydrophilic part and a hydrophobic part, they will preferentially adsorb at the interface. So if the concentration in the bulk, if the concentration at the interface is very high, then there's a much higher chance that surfactants at the interface will dissolve into the bulk. And similarly, if because of various factors, for example, there could be a flow which could be driving the surfactants at the interface. If there is a depletion of surfactants at the interface, then surfactants from the bulk are likely to adsorb at the interface. So there is also kinetics of adsorption and desorption that happens. So when you deal with surfactants, one also needs to know how surfactants are adsorbing and dissolving at the interface. And we will have two separate evolution equations, one for equation at the interface for Ci, so that would be Ci, and one in the bulk, that is Cb. Okay. Note that we are not writing down equations for individual surfactant molecules or transport of individual molecules. We are determining what is the concentration of these surfactants in a region given in a small volume, and we are writing down concentration evolution equations. So these are typically advection diffusion equations, and typically with a source and a sink term, because the source and the sink term will take care of adsorption and desorption at the interface, between the interface and the bulk. And again, for various surfactants and combination surfactants and fluids, these relationships are well documented in the literature. Gamma is a function of concentration. Further, one can actually determine this using various instruments. Okay, so that sort of more or less concludes the main part of the discussion here, which is what are the equations and the boundary conditions or jump conditions at the interface. Now, one small thing that I want to touch upon is that if you look at the interface, we have normal vectors. For example, we have terms like n dot tau dot n, and in the tangential stress balance we have n dot tau dot t. Now, what is this n, and what is this? How do I determine n and t? So I'll give you a simple example of how do we determine n. There are several ways to do this, but let's consider a simple two-dimensional example. Okay, so we will be looking at examples of this kind. So therefore, it's useful to just quickly understand how do we determine n. So for example, let's consider a 2D system like this. We have the xy coordinates, and we have some arbitrary interface like this. Now, I want to the interface itself is defined using in the following way. Any point on the interface is given by the equation y is h of x comma t. That's the equation of this interface. So in other words, equation of the interface is y equals h of x comma t, right? Now we can define a new function. Let's say we call it as capital F, okay, which I'll define it in such a way that f of x comma y comma t is 0, such that this function f is identically 0 on the interface. If you're above the interface, f is greater than 0, and if you're below the interface, f is less than 0. Okay, so we could think of something like this, where below the interface I call it minus, and above the interface I call it plus, and my goal is to determine this normal vector n. Okay, so and maybe even we could even say I want to extend my goal and say I want to determine the tangent vector too. So this is my goal. Okay, so I've defined this f. However, I ensured that f is identically 0 at the interface. Okay, I can do this by just simply saying f of x comma y comma t is explicitly written as y minus h of x comma t. This is equal to 0. But remember, the interface is only on that blue line, but the function f can has a value everywhere in the domain in this region. So f is less than 0 in below the interface in the minus region, and f is greater than 0 in the plus region, and therefore the normal vector, unit normal, is, which we refer to as n hat, is just gradient of f by magnitude of this gradient. Okay, so that's my basically my normal vector, and I can easily calculate the gradient of f. Gradient of f is del f by del x I hat j hat. Okay, where I and j are the unit vectors in the x and y directions. Del f by del x can easily be determined, that is minus dh, or sorry, partial h by partial x. I had to write partial derivative because h is a function of both x and t. Okay, plus, what about del f by del y? It is just 1 times j hat. Okay, and the magnitude of this gradient is 1 plus del h by del x whole square. Okay, so we can simply use shorthand notation. We'll call it as hx of I plus j, and this is 1 plus hx square, and therefore now I have the normal vector would be minus hx I hat plus j hat by 1 plus hx square. That's my normal vector. Okay, I would like you to try to derive the tangent vector yourself. The tangent vector will turn out to be I hat plus hx j hat 1 plus hx square. So if I know in 2D, if I know the expressions for, if I know n and t, and let's say I know the stress tensor sigma, which is minus p times I plus tau, this would be plus tau, that is, so remember this tau itself is minus p times I plus 2 mu s, where s is the strain rate tensor. Okay, so just continuing the discussion in for 2D, just for 2D flows. Okay, this will be del u by del x. Here we'll have del u by del y plus del v by del x. We have, it's a symmetric tensor, and finally we have del v by del y. We have all these terms. Okay, now you can calculate easily n dot sigma dot n, which will be nx ny sigma xx, sigma xy, sigma yx, and sigma yy times, I am illustrating this as matrix multiplication for those students who may not be very comfortable with index notation. This is also very easily done using index notation. Okay, and if you do this, you should be able to verify that this term here, n dot sigma dot n, will be minus p plus 2 mu of hx by 1 plus hx square times ux, where ux stands for del u by del x, partial u by partial x, plus 1 by 1 plus hx square by minus hx by 1 plus hx square uy plus vx. But we can further recognize that the u derivative of x and the v derivative of y are related to each other through the continuity equation, right? Vy is minus ux. This is again, remember, this is only in 2D. Therefore, I get something like n dot sigma dot n is minus p plus 2 mu, which will be hx square minus 1 by 1 plus hx square ux minus hx by 1 plus hx square uy plus vx. So you should get something of this nature. This is basically my the normal stress balance. One can similarly work out the tangential stress balance at an interface once you know the normal vector and the tangential vector. Okay, so so with this, I'll stop the discussion on governing equations. What we will do in follow-up lectures is to look at capillary statics, and then we will look at dynamics. Okay, so once we put all these equations and everything together, we can branch out into two parts. One is capillary statics, where we say I'm going to look at only those class of flows where there is no motion, and then we look at dynamics, where there is motion and we'll have to deal with these full set of equations. We will look at simple problems where we may make a variety of different assumptions. For example, I may say that the viscosity of the upper fluid is negligible. That's one kind of assumption. We could also say that the upper fluid is actually passive, which means that it does not contribute to the dynamics at all, but it's only there to generate an atmospheric pressure. For example, a large class of problems, such as, let's say, coating flows, problems in thin films. So these are all what are called as free surface problems. Free surface flows are problems where there is an interface, so you have to deal with surface tension, but you don't have to deal with it as a two-phase flow, but as a single-phase flow. Okay, where you don't actually worry about solving for mass and momentum balance in the other fluid. Do you say that the other fluid is only providing me a constant pressure? It is passive. In any other way, it does not affect the flow in the bottom, except providing a constant pressure. So we will deal with these kinds of problems, the free surface flow problems as well. So in the next couple of lectures, we'll be looking at problems where there is no motion at all. This comes under the subject of what is called as capillary statics. All right. So thank you.